Thank you very much for the invitation. I have to say I'm okay. Okay, I'm okay. Um, yeah, so I'm going to talk about classifying some open toric domains. It's very early in the morning here, so I had to put some memes in to liven it up. Although then I deleted most of them because I didn't want to offend anyone. Anyway, so I'll first state the main result, and then I'll tell you about some invariants which we'll use to prove the results, which make certain barcodes out of open domains, and then I will compute these barcodes for the domains that we're trying to classify, and then prove the result. Like very recently, Xiaodi Tang and Jun Zhang sent me a draft of a paper where they have what looks like a simpler proof of the same result, although I had some questions about it and there wasn't enough time to resolve them. Anyway, so they might have a simpler proof for the result, but I think that the method I'm going to tell you about should be applicable to more problems like this. So even if the application is a little too simple, I want to show you this method, and it's a cute example of this method. Okay, so the general question we're interested in is classifying bounded open sets in R2N up to symplectomorphism. So, well, that's sort of completely hopeless. You can take an open set, you can take any Hamiltonian vector field and move it around in all sorts of ways. So more reasonable question you could try to ask is pick some family of examples and say, okay, can I at least classify this family of examples or tell some of them apart, even if completely classifying things is pretty hopeless. There are also related interesting questions about trying to understand the geometry of the space of all open sets modulo symplectomorphism with various metrics like symplectic Banach Maser distances and things like that. And that's also a little related to what I'll be talking about. So here's some of what's previously known. So let's consider a sort of nice kind of bounded open set where the boundary is a smooth hypersurface, which is transverse to the radial vector field. Sometimes people call that star-shaped. And then if it's transverse to the radial field, then the standard Liouville form on R2N restricts to a contact form on the boundary of X. So it has an associated ray vector field. And let's further assume that this ray vector field is non-degenerate, that is all of its periodic orbits are non-degenerate. And that will hold at least for a generic hypersurface. And let's let P of the boundary of X denote the set of all of these periodic orbits or ray orbits. And if gamma is such an orbit, then it has a symplectic action, A of gamma, which is its period under the ray flow, or equivalently the symplectic area of a disk in R2N, whose boundary is gamma. And it also has a Conley-Sanger index, which is an integer. And here I compute it with respect to a global trivialization of the context structure on the boundary of X, which I can find since it's just a sphere. So back in the 90s, there's a paper by Seelebach, Flor, Hofer, Wysotsky, which proved that the actions and Conley-Sanger indices of the ray orbits are symplectic invariant. So the way you can say it is if X and X prime are two of these nice open sets with smooth star-shaped boundary, and if they're symplectomorphic, then the multi-set of pairs of action of an orbit, comma, Conley-Sanger index of an orbit is the same for both domains, which means that for any possible pair of a real number and an integer, the number of times that it appears for both domains is the same. And the idea of their proof is they look at symplectic homology in a narrow action window. So you look at sort of the subcomplex of symplectic homology, where there's some upper bound on the action of Rabe orbits that you allow, and then you you mod out by or throw away Rabe orbits with slightly smaller action. So that homology can see which Rabe orbits exist with action in that narrow window, and it's also graded, so you see the Conley-Sander indices of the orbits. So that's a nice result. Now, let me tell you about the domains I'm going to study. So these are open toric domains. So let omega be a bounded open set in the first quadrant of the plane, pairs of positive real numbers. And I mean open with respect to the topology on the quadrant. So these are going to include pieces of the axes and the origin, even though it's not an open set in all of R2. It's still an open set in this subspace. So for given omega, we define the toric domain X omega. That's the set of points Z and C2, such that pi times absolute value Z1 squared, comma absolute value Z2 squared is in omega. So this pi absolute value Z1 squared, absolute value Z2 squared is the usual moment map, which generates the usual torus action on C2. Now, an open convex toric domain is an open toric domain as above, such that if you take the set omega and then look at its reflections across all of the axes, then you get a convex set. Here's a picture. So on the upper left, that's an omega, which gives a convex toric domain. On the upper right, I've drawn an omega. So the set omega itself is convex, but then when I reflect it across the axes to make a larger set, that set is not convex. So this omega does not satisfy my definition of convex, although some other authors do consider that to be a convex toric domain. Like in some papers by Dan Christopher Gardner, this would be considered a convex toric domain. The one sort of difference in this case is that the convex toric domain is on the left. That's dynamically convex. So all of the Rabe orbits of Conley-Sander are next at least 3, while these sort of not quite convex toric domain on the right has Rabe orbits could have smaller, arbitrarily negative Conley-Sander index. There's also a slight misnomer in the terminology. So a convex toric domain is not the same as a toric domain which is convex. I apologize for the bad terminology. It is convex, but you can make toric domains where the omega is not convex, but the associated toric domain is still convex. Should maybe call it like torically convex or something. And so I apologize for the bad terminology. As a basic example, I don't really need this, but if you take a triangle, so it looks like this. It has edges along the axes going to the point A, 0 and the point 0, B. I didn't indicate it in the picture, but the diagonal of this triangle, that's not an omega, so this should be like a dotted line. But these pieces of the axes are an omega. So that is in inequalities is described this way. So x is greater than or equal to 0, y is greater than or equal to 0, and x over a plus y over b is less than 1. And then the corresponding toric domain is the ellipsoid EAB, which is given by this inequality. So there's been a ton of work studying ellipsoids, polydisks, other toric domains. usually asking questions like, when can one of these domains be symplectically embedded into another one of these domains? There hasn't been that much study of when is one of these open domains symplectomorphic to another. Okay, so here's the theorem. So let x omega and x omega prime be two open convex toric domains. And I also have to assume a genericity condition. I'll tell you a little later precisely what that condition is. It's not that bad. And suppose that these open domains are symplectomorphic, then the omegas have to be the same or reflected. So there's certainly a symplectomorphism of R4, which exchanges the complex coordinates Z1 and Z2. So which corresponds to reflecting omega about the line y equals x. But anyway, if the domains are symplectomorphic, then they're the same or equal up to that reflection. And as I mentioned at the beginning, Shodi, Tong, and Jun Zhang have some work in progress proving something similar. There is a precedent for this. So there's the 1994 thesis of Moati, and he proved that this result holds under the assumption that the boundary curves of omega and omega prime. So here I mean, I don't mean the part of the axes, I just mean the curve, part of the curve that's not on the axes. If those curves are real analytic, and why does he use real analytic? Well, what he actually shows is that you can determine the germ of the boundary curve where it intersects the line y equals x from certain symplectic invariants. And these symplectic invariants are some capacities defined using equivariant symplectic homology. They're very similar to capacities that Jean Good and I defined much later. And they're given by the same, they're calculated by the same formula for these examples. The difference between the definitions is that Moati used an older version of equivariant symplectic homology due to Viterbo, and Jean Good and I used a newer version due to Bourgeois and Wancha. But the idea is similar. They're probably isomorphic, but I don't think anyone's proved that. So yeah, so I didn't know about this paper at the time that Jean Gut and I did our work. I learned about it later. So either Moati's thesis was way ahead of its time, or I am way behind my time, or maybe both. And we can ask if this generalizes to higher dimensions, even if you assume real analytic or something. I don't think that's known. I need another definition. So if x omega is an open convex toric domain, and if a and b is a pair of non-negative integers, there's an action, which is just a real number. And this is the maximum of ax plus by, where the point xy is in the closure of the domain. I'll draw a picture. So here's omega. So can you see my cursor when I move it around on the screen? Yeah, okay, good. So here's omega. This is the boundary of omega. This is the vector a comma b. So what you do is you take a line perpendicular to this vector a comma b, and you sort of move it down until it touches the domain where it's tangent. It's tangent at some point xy, and that xy is the point that realizes this maximum. Oh, sorry, this maximum. And then we just take the inner product of AB with xy. Now, a remark which we'll need later is this line here, which I drew perpendicular to AB, it determines a half space, HAB. So I'm going to let HAB denote the half space to the lower left of this line, at least to the part of the upper quadrant. And because omega is convex, it's the intersection of all of these half spaces. And you can show that you actually don't need to know like all of the half spaces where this vector is a real vector. You can just restrict to the case where it has rational slope. So if I define HAB to be this half space, then omega is the intersection over all pairs of non-negative integers, not both zero, of those half spaces. So if you want to determine the domain omega, you just need to know what are these actions. So I need to know specifically the function which assigns to each pair of non-negative integers a and b its action. Now, why am I calling it the action? Well, that's because this comes from the Rabe orbits. So, sorry, the slide is a little crowded, but so if boundary plus omega, this is the boundary curve of omega, not including the axes. And just to simplify this discussion, let's suppose that that curve is strictly convex and that where it touches the axes, it's not perpendicular to them. So you can then calculate the Rabe vector field on the boundary of x omega. So the Rabe orbits consist of the following. So first of all, where z2 equals 0, there is a Rabe orbit, which I call E1, 0. So on the picture, that's over here. This is the inverse image of this point under the moment map is the orbit E1, 0. And that is an elliptic Rabe orbit. Its Conley-Sanger index, actually, I lied a little bit. Sorry, the Conley-Sanger index is 3, assuming that it's the boundary curve is not perpendicular, but almost perpendicular. Wait, no, I'm not lying. I'm sorry. That's totally fine. I was worried about the multiple covers of it. Sorry, it's very early in the morning. Okay. Anyway, so this is Conley-Sanger index 3. Its action is the number A10 of omega, which is a clumsy way of just writing the x coordinate of this point. So its action is the x coordinate. Likewise, on the y-axis, there's an elliptic Rabe orbit where z1 is equal to 0. Its action is the y coordinate where I hit the axis, and its Conley-Sanger index is also 3. And then in the interior of this boundary curve, if I have some point where the normal vector has rational slope, then that moment map image, it's a torus, the Rabe vector field moves along the torus with constant rational slope, with the result that it's foliated by Rabe orbits. So it's a more spot circle of Rabe orbits. Each of these Rabe orbits has symplectic action A, which is the reason why I defined it that way. And if you would rather have a non-degenerate contact form, then you can perturb that circle of Rabe orbits using a Morse function on that circle with one maximum and one minimum. And that turns it into an elliptic orbit, which I denote by EAV, and a hyperbolic orbit, which I denote by HAB. And their Conley-Sanger indices are given by these formulas. So the elliptic one, there's a typo. This, imagine there's a 2 here. So the Conley-Sanger index of EAB is 2 times A plus B plus 1. And the Conley-Sanger index of HAB is 2 times A plus B. Now, if we go back to this Zilibach-Fleurhofer-Wysocki result, it doesn't quite apply as stated to a toric domain because the Rabe flow is degenerate on the toric domain. But you can modify their action. You can still look at symplectic homology and action window. And each of these tori is going to contribute a rank 2 subspace of the symplectic homology. So the upshot is it follows from that kind of argument that these action values, the AAB, given a constraint A plus B, which corresponds to the Conley-Sanger index, this multiset is a symplectomorphism invariant. So, so I know what the number, symplectic invariants tell me what are the numbers AAB. And the genericity condition that I need is to assume in the main theorem is that for a given k, these action values A, B are distinct. Maybe this can be dropped, but I'll need it at one point in the proof, as you'll see. So if we want a classification result, this isn't quite good enough because I don't know which of these, like the symplectomorphism invariant is just a list of numbers, and I don't know which number corresponds to which orbit. So I actually need the function setting the pair AB to its action AAB. It's not enough to just know what's the set of values of that function. So that's the task that we're confronted with, is to see that function from symplectic invariance. I will remark, we'll need this a little bit later, that the capacity, either defined the way John and I do it or by similar methods, is the minimum of these numbers where A plus B equals K. So are there any questions so far? I've heard maybe some distant voice, but I couldn't hear. Okay, I guess no questions right now. All right, so what about the foundations of this theory? So there are sort of two basic packages we can use. We could either use equivariant symplectic homology or cylindrical contact homology. Now, cylindrical contact homology has a nice simple definition, and we can understand it pretty explicitly. The only problem with it is it only has a completely rigorous definition in some limited cases. But anyway, those cases do include the cases relevant to us. And alternatively, one can use equivariant symplectic homology. So there's so the paper by Bourgeois and Owansha gives an argument that these two theories are isomorphic when they're both defined, but it assumes some very strong transversality hypotheses which don't hold in our situation. But anyway, we would expect these to be isomorphic. But the equivariant symplectic homology is defined much more generally. But the definition's a lot more complicated and it's more awkward to work with. So basically what I'm going to do is I'm going to explain things from the point of view of cylindrical contact homology because that's simpler. Although this depends on one unfinished paper. And if you are not comfortable with that, then everything can be done with symplectic homology instead. It's just more complicated. Okay, so cylindrical contact homology. So let's consider an open domain in R4 where the boundary is smooth and the rate flow is non-degenerate. So this is the cylindrical contact homology. It's the homology of a chain complex, which is generated over Q by Rabe orbits, which are good. All of the Rabe orbits we're going to be talking about are good. A bad Rabe orbit is one which is an even multiple cover of some other Rabe orbit whose Conley-Sanger index has opposite parity. The grading I'll take is the Conley-Sanger index -1. The differential counts J holomorphic cylinders in R across the boundary of X for a suitable almost complex structure J, which are asymptotic to two different good Rabe orbits on the top and the bottom. And you have to count them with appropriate signs and combinatorial factors. And this definition is due to Eliashberg, Giventhal, and Hofer. In general, there are problems with finding J satisfying sufficient transversality for this to be defined. However, in the paper with Joe Nelson, we proved that in the special case of dynamically convex contact 3 manifolds, and that includes non-degenerate perturbations of boundaries of convex toric domains, the differential really is well defined and it satisfies d squared equals 0 for generic J. There's one paper we still need to finish to prove all the invariance properties you want with coordinate maps. So we did this completely in the hypertight case when there are no contractible wave orbits at all, which won't help us today. And then in the dynamically convex case, you have to sort of add one correction term with a bit of obstruction bundle gluing. The positive S1 equivariant symplectic homology in the version defined by Bourgeois and Awacha, it's the homology of a chain complex over Q. You could actually do this over Z if you want, but I want to do it over Q. It has a lot more generators. So for every wave orbit gamma, and for every non-negative integer k, there's a generator u to the k times gamma check and u to the k times gamma hat. And the wave orbit doesn't have to be good, it could also be bad. And the differential counts solutions to a PDE, which is a coupling of the Hamiltonian Floer equation and the gradient flow equation for Morse function on the classifying space of S1. And then you can use a spectral sequence argument to show that, at least if you use Q coefficients, this isn't true with Z coefficients, but with Q coefficients, this is the homology of a chain complex with one generator for each good wave orbit. So that looks more like cylindrical contact homology. And it's defined for star-shaped domains in any dimension, and you would expect it to agree with cylindrical contact homology when it's defined. Now, if you want to know what is the homology, well, if I have a dynamically convex domain, or actually any star-shaped domain, the homology is very simple. There's one generator in every positive even degree, and that's it. We'll see later one computation of this. So that's not really going to tell us anything about that can tell different domains apart. To do that, we need to use the filtered cylindrical contact homology, and that takes into account more information with the actions of the wave orbits. And there's an analogous story using equivariant symplectic homology instead, if you prefer, but I won't go into that. So what is this filtered cylindrical contact homology? So for each, oh, this is another typo, excuse me, where it says L is less than 0, that doesn't make any sense. This is L should be greater than 0. So for each positive real number L, we can just look at the subcomplex generated by wave orbits with action less than or equal to L. And the differential preserves this subcomplex because the standard calculation, which shows that the differential decreases the symplectic action. And I denote the homology of this subcomplex by CH less than or equal to L of X. Now, if I have a bigger real number, L prime, then there's an inclusion of chain complexes, and that induces a map on homology. This map on homology is not necessarily an inclusion. And I denote this by CH L prime comma L. And this is, we sometimes call this a persistence morphism. So this structure consisting of all of these vector spaces, CH less than or equal to L, and all of these maps, CH L prime comma L, is an example of what one could call a Z-graded persistence module. So everybody has a slightly different definition of what's a persistence module, but what I mean by this is basically you have these finite dimensional vector spaces, you have these maps. These maps have to be functorial. So if I had a third value of L, then these maps would compose. And you assume some finite dimensionality. So you want to assume that these vector spaces are finite dimensional and that there are only finitely many values of L where this map between nearby values of L is not an isomorphism. And from that, you can make a barcode. I'll show you an example later. And then the further structure we have is that if I have a symplectic embedding of x into x prime, and let's assume that the image of the closure of the image is contained in the open set x prime, then there's a cobordism map, otherwise known as a transfer morphism, from CH of the bigger domain to CH of the domain that's embedding into it. And it's a morphism of persistence modules, which means it maps the CH less than or equal to L to the CH less than or equal to L, and it respects these persistence morphisms. So that's the structure we've got. Now, I would like to extend this to give an invariant of any open set where the boundary is not necessarily non-degenerate, or maybe not even smooth. So how am I going to do that? Well, I need, for this to work, I need to at least assume that it's exhausted by dynamically convex domains, like we just discussed, or images of them under symplectomorphisms. So you could say, well, let's take a sequence of these convex domains, which is converging to the boundary, and let's take one which is sufficiently close and look at CHL of that. Then we could try to prove that that's independent of choices, but that's kind of a mess, because if we're approximating the domain, we're changing the symplectic actions of everything. So I don't like that. So we need another meme. So instead of doing that, the easier thing to do is to just take an inverse limit, and everything is going to work much better. So here's what we do. So if X is a bounded open set, I'm going to define CHL with a little circle on it over it. That circle is supposed to indicate that it's the invariant of open domains. As an inverse limit of CHL of W, where W is a non-degenerate dynamically convex domain, together with an embedding into X. And what that means, so what is an element of this inverse limit? That means that for every W and every symplectic embedding into X, you pick an element of CHL of W. And those different elements have to be compatible under transfer morphisms. So if you have W and W prime, and if W prime is a subset of W, then the element that you chose for W has to map to the element that you chose for W prime under the inclusion of W prime into W. So that sounds very complicated, but you can show that if your domain was already nice, if it was non-degenerate with smooth boundary and dynamically convex, and this just agrees with the definition you had before. And you can also show that you have persistence morphisms and transfer morphisms like you did before. And you can do this for other kinds of contact homology too. You could do it for symplectic homology, you can do it for ECH, so it's a useful construction. So the claim is that you take, okay, let me not say the claim yet. Okay, so we've got these vector spaces which depend on L, and we've got these morphisms. This might not quite satisfy the usual definition of persistence module, because if your domain X is nasty enough, then these vector spaces could be infinite dimensional, and there could be infinitely many places where these maps are non-trivial. Although we will see that it is a persistence module in the case of a convex toric domain. And the inverse limit construction gives a very clean proof that this is symplectomorphism invariant. So this is explained in my recent paper where I used this to define zeta functions. Any questions about that?
Maybe I have a question. So, do your model satisfy the condition that images are finite dimensional of the persistence morphisms? So
Um,
spaces could be not, but image of kind of.
I think that might be true. I have to think about that.
Yeah, so then it's kind of it's called QTame, and this is standard property in a slightly kind of more fancy definition of persistence models, which people in persistence use.
Okay, thank you. I'm still a beginner at all of this. So this started when Jean Gut organized a conference on persistence modules, and I felt that, like, for homework, I had to do something with them. Okay. Okay, so now let's talk about the case of a convex toric domain. So I'm going to define a model chain complex. So like the toric domain itself, its boundaries degenerate, so I don't really have a well-defined chain complex exactly, but let's ignore that issue, and so if we did have a well-defined chain complex, this is what it would be. So the generators consist of, for every pair of non-negative integers a and b, which are not both zero, I have a symbol EAB and a symbol HAB. You can think of these as representing elliptic and hyperbolic orbits obtained from perturbing four spot circles of Rabe orbits. The grading of EAB is 2 times a plus b. The grading of HAB is 2 times a plus b minus 1. The action of both of these is this number AAB of omega, which I defined before, which we're trying to recover. And the differential of EAB is 0, and the differential of HAB is EA minus 1b plus EA comma b minus 1. So let me draw a picture of this to make it a little easier to understand. So here's the chain complex in the first few gradings. So at the bottom, in grading 2, I have E10 and E01. Then in grading 3, I have H11, and then it goes up like this. Note that these H generators cannot have either of the subscripts equal to 0, because the E10 and E01, that's an isolated elliptic orbit. It's not coming from a Moore spot circle. So you can see from this picture that the homology is Q in every positive even grading and 0 otherwise. And any of these E's is a cycle which generates the homology, because these arrows prove that all the different E's are homologous. Another remark is that all that matters is that these arrows are non-zero. The actual coefficients don't matter, because if you look at the graph where the vertices are the generators and there's an edge when there's a non-zero differential between them, this is a union of trees. So you can change the coefficients and you get an isomorphism of chain complexes. So in the differential here, I put these coefficients as 1. In cylindrical contact homology, they're probably something else, but I don't care. I just care that they're non-zero. So associated to this chain complex, there's a persistence module, where the vector space associated to L is the homology of the subcomplex generated by generators with action less than or equal to L. It's an exercise to check that this differential decreases the action. If it didn't, then I'd be in trouble. And then the theorem is that there's an isomorphism of persistent mod. So the invariant of the toric domain, which is not, well, as Leon had said, in general, it's some kind of generalization of persistence modules, but in this case, it's an actual honest persistence module, and it's isomorphic to the one coming from this model chain complex. And you can do a similar calculation for positive S1 equivariant symplectic homology, and you get the same answer. And K-Erie has a more general conjecture on the filtered equivariant symplectic homology for more general toric domains. And my understanding is that this is consistent with that conjecture. Okay, so how am I going to prove the theorem? So I'm trying to prove, sorry, not the main theorem, but what I just said about the isomorphism of persistence modules. So for any given grading K, I can perturb to make the boundary non-degenerate, and so that all the Rabe orbits, at least up to grading K, are as described in the previous slide. I can't really do this for all Rabe orbits at once, but if I up to a given grading K, there are only finitely many more spot circles of Rabe orbits, and I can perturb each of them individually. And then maybe there's some other weird orbits of very large action grading, and I don't care about them. Okay. So we need to show that if you choose a suitable almost complex structure J on R cross Y, then the differential is given as described. In fact, the differential is the same regardless of such J, which you wouldn't expect in general, but is true in this example. So the first step is we can show that certain differentials have to be zero using intersection positivity. So let me start at this second bullet point. So suppose I have two generators, but neither of them is equal to E10. And suppose there's a non-trivial differential. In other words, suppose there's a holomorphic cylinder going from gamma to gamma prime. So this holomorphic cylinder has to have positive intersections with the trivial cylinder given by R cross E10. And you can compute that intersection number. It's just the difference of linking numbers. So the linking number of gamma with E10 has to be greater than or equal to the linking number of gamma prime with E10. Now we can compute all of the relevant linking numbers here. The linking number of EAB or HAB with E10 is just B. So that means if this differential is non-zero, then the B subscript has to decrease or stay the same. And a similar argument shows that the A subscript has to decrease or stay the same. And then if you look at the formula for the grading, this rules out almost everything. The only possible differentials you could have, there could be differentials from EAB to HAB. So this is where the subscripts stay the same. Or you could have differentials from HAB to EA minus 1 comma B or to EAB comma B minus 1. So in other words, you can decrease one of these subscripts by 1. If you decrease subscripts any more than that, then the grading difference is too big. Can't be part of the differential. Now, there are in fact holomorphic cylinders from EAB to HAB, but there are two of them and they cancel. So this is a standard picture for Moore spot theory. So I have this Moore spot circle of Rabe orbits. I perturb it using a Morse function, and then the flow lines, sorry, the cylinders between the non-degenerate orbits correspond to flow lines of this Morse function. And there are two of those, they cancel, unless you use some twisted coefficients. So the last thing that we need to do is show that these remaining possible non-zero differentials actually are non-zero. You might be able to directly construct the holomorphic cylinders that you need. So Taubes in his papers on holomorphic curves in R cross S1, cross S2 has some relevant methods for that. I did not attempt this. We can give a kind of a short and more indirect argument to get the same conclusion. So we know by invariance of cylindrical contact homology that the homology in each positive even grading is Q. And then it's enough to show that each of these EABs represents a non-zero homology class. So if you, I didn't completely explain it, but if you go back and look at this picture, if you delete any of these arrows, then then some of one of these. Oh gosh, I actually did do that because there's another typo. So there's supposed to be an arrow here from H13 to E03. So you can see if I delete that arrow, well, now the homology is too big. But there are other ways you could imagine deleting the arrows where, like if I deleted this arrow and not deleted this arrow, then E03 would become null homologous, and that would also be bad. So if all of the EABs are not null homologous, then the arrows have to look like this. Now, you can do another intersection positivity argument to show the differential doesn't depend on J or omega. So to prove that EAB is homologically non-trivial, I can find a single omega where that's the case. But I can find an omega where the action of EAB is less than the action of all of the other EABs to have the same grading. And you can sort of mimic the construction of the capacities of myself and Jean-Claude in their calculation to show that this action is this capacity of the domain. So it has to, that homology class has to be non-zero, otherwise the action would be bigger. The capacity would be bigger. So that's the sketch of the proof for the calculation. Maybe I should ask if there are any questions about all of that. Okay, so if you believe that, then now we can compute the barcode. So in general, this is a non-trivial algebraic calculation. If you know the chain complex, and well, I guess I should recall what the barcode means. So for any persistence module, it's isomorphic to a canonical sort of simple persistence module in which is a direct sum of two-term chain complexes where there's a differential from one generator to another, together with some isolated generators which have no differential. So for a two-term complex, you make a bar, which is the interval between the action of the bigger generator and the action of the smaller generator. And for an isolated generator, you make an infinite bar, which starts at the generator and goes up to infinity. So the barcode's just a multi-set of intervals. And it's, in general, there's some complicated algebra to compute the barcode given the chain complex. But in this case, there's a lemma which simplifies the calculation a lot. So if we fix the k, which determines the grading, then you look at the function sending a number a to the action of a comma k minus a, and it has a convex function of a, little a. So it means the function, like it starts going down, it reaches its minimum, and then it goes up again. So from that fact, you can deduce that the barcode is quite simple. So there's an infinite bar, whose endpoint is the action AAB, where this is the minimum of AAB for the given grading K. And then in addition to that, there are K finite bars. So these pair up the numbers. This is another typo, I'm so sorry. This should go from AK1 to A1K. And they pair up with these numbers AK0 through A0K with the minimum emitted, respecting the order. So I'll draw you a picture to show what that looks like. So here's what it could look like. So this is the lower part of this picture. This is grading 10. On the upper part of this picture, this is grading 11. And this is an example where the minimum action in grading 10 is given by the action of E23. And this minimum grading generator, its action is the capacity. And there's an infinite bar. So whenever you see an infinite bar, that's some capacity or spectral invariant. And then the bars just pair up all of the other generators. Now here I have these actions correspond to H generators. So there are no zero subscripts here. So there's like A51 through A15. And these are paired up in order with the actions A50 through A05 with A23 omitted. And these are the actions of the elliptic orbits. And algebraically speaking, what I really need to do is present an upper triangular change of basis. So A14 is not literally corresponding to E14, it's really corresponding to E14 plus E23. So this is indicating my change of basis, which turns the chain complex into this sum of two-term chain complexes. So we can use this barcode to prove the theorem I stated at the beginning about the classification. So here it is. It's a one-page proof if you make the page sufficiently cramped. So let X omega be a generic open convex toric domain. And I need to prove that some symplectic invariance of X omega, in this case, obviously, it's going to be the barcode that we've been talking about, but some symplectic invariants recover the function which sends a pair A, comma B to the action A, AB. And of course, I'm only hoping to prove that I recognize X omega up to reflection of omega. So I need to prove that I recover this function up to a possible switching of A, comma B with B, comma A everywhere. Now, to get started, I know what the numbers A10 and A01 are, because these are the only grading two endpoints of bars. I know these numbers as an unordered pair. So it's enough to show that if I actually know the correct order, so if I know the ordered pair of numbers A10 and A01, then that ordered pair, together with additional symplectic invariance of X omega, determines the function that I'm looking for, sending AB to its action. So we'll prove this by induction on K, which is A plus B. So suppose that K is greater than or equal to 1, and suppose I already know the function sending AB with A plus B equals K to its action. And my genericity hypothesis was that this function is injective. That's going to be important now. Now, we saw in the previous slide that the barcode pairs up these values, A, B, with the minimum value removed, with the numbers A, B of omega, where A and B are positive and A plus B is K plus 1 in order. So that means if I know this function, then I determine this function where K is 1 bigger. Because if I want to find the function for some AB with K1 bigger, well, I look at the bar that touches this. I know that's going to be connected to sorry, I said that backwards. Let me try again. So going back to my picture, like I know this action, so I just have and these action values are distinct. So I look at the bar, there's going to be a unique bar whose lower endpoint is this action, and the upper endpoint of that bar is now going to be the A33 that I'm looking for. So the bars tell you how to connect all the different action values together and recover the function. Now this didn't quite tell me what the action values are if A or B is equal to 0, but that's easy because those actions are just multiples of the numbers A10 and A01 that I already knew at the beginning. And that's the proof. Any questions about that? Okay. So here's some further questions that might be interesting. So first of all, that genericity hypothesis I made is a little unsatisfying, so it'd be nice to remove it. More generally, we could say, can we classify other open toric domains in R4, which are not necessarily convex? So like you could take some sort of wiggly curve in the upper quadrant of R2 and look at the toric domain and say, does that curve determine, or sorry, does the open toric domain determine that curve after reflection? And I think this method might be useful for that because you sort of expect the holomorphic cylinders to go between sort of nearby, to go between orbits corresponding to nearby points on this curve. So the bars in the barcode might be able to sort of connect up the orbits of different gratings and recover the curve. You can also do, so the invariant I described with the inverse limit, you can do for other versions of contact homology. So like embedded contact homology also gives you a barcode. I don't know what geometric information one can get out of that. And one could say, can we generalize to toric domains, maybe generic convex ones in higher dimensions? And if we can't classify them completely, can we at least tell some of them apart? Thank you.
Any questions?
Yeah, I have a couple of questions. So, can you please go back to the slide with the arrows describing the differential? So, yeah, there is something that I didn't understand. So, if you remove the arrow from H13 to E03, then you have E03 is a generator, but doesn't it kill all of the others are now 0, right?
Right. I think I said the wrong thing before. So let me try again. So here, where by some typo I've deleted that arrow. Now E03 is a homology generator, and then the rest of this chain complex is acyclic. So every other one of these E3 zeros, is that right? Yeah, because this is
So you have one generator.
Yeah, so there's one. So the homology still is rank 1, which sort of has to be by. Actually, that's not true either. Anyway, yeah. So here the homology still is rank 1, but like E12 is null homologous because it's the differential of H13, and these others are null homologous also. So I ruled that out by showing that actually all of these, each individual E generator has to be non-trivial homology.
Okay, I'm sorry. I thought that the contradiction you showed by eliminating one of the arrows was to say that now the homology is not correct because you have two generators. But maybe I misunderstood.
Yeah, so the contradiction, if you remove this arrow, the homology is still correct, but these generators are null homologous. but I argued using the capacities of these generators are not homologous.
Okay, thank you. And my second question is, you essentially showed something which is just combinatorial, right? So, I mean, you can ask the question about this line in R2 with its normals and heights, and then it's just a combinatorial question whether the map AB goes to the action describes the set of all actions where A plus B equals K describes the graph. I mean, can I ask this question without any symplectic, without any connection to symplectic geometry, right?
Right.
So you actually proved this like combinatorial argument using symplectic homologies, symplectic homologies, but it sounds like it's a very nice application to flow homologies to prove this combinatorial argument. But I mean, can't one find like a more direct approach to proving this? Or
sorry, I'm having a little trouble hearing what you're saying. So I didn't quite understand what you mean by the combinatorial statement. I mean, there's a sort of elementary observation we made early on, which is that omega is the intersections of these half spaces, which we then use later. But you might maybe mean something else.
Yeah, so what I meant is that what you proved is, I think, maybe I'm wrong, but I think what you proved it's that if you have a line in R2, and then you can find the normals that have integer coefficients and calculate the action using this formula with the xy, the inner product of xy and ib, and then whether if you know the set of actions when a plus b equals k, then does it recover this graph?
Right. Yeah. So you say if I just.
So in this question, there are no symplectic things at all.
Right. Okay. Yeah. So you could say, all right, if I just know this multiset, can I recover the domain? So that's actually what the paper draft by Tong and Zhang was doing that, although I didn't completely understand one point in the argument. So it is possible that maybe one can just recover the domain from this multiset without going through all the rest of what I did. In which case, if that's true, then my argument was unnecessarily difficult. But I think this technique could prove some other things, which would be harder.
Yeah, I'm actually mentioning this from the other direction, that maybe you can, I mean, take combinatorial questions and try to solve them using symplectic methods.
I see. So I don't think I gave a proof that this multi-set determines the domain, because what I showed was that this multi-set plus some additional information coming from these barcodes determines the domain.
Okay, thanks, Asaf. Any other questions?
I have a question. At the end, you get this barcode, right, with actions and gradings. And
Yes.
somehow from this barcode, you reconstruct the function. So what is the reconstruction procedure? So do you have kind of formulas, some functional defined on barcodes, which given barcode produce your function, or something kind of. So somehow the very ending I missed.
So let's go back to the picture. So okay. So we're okay. So we're trying to determine this function here, since inputs A, B, and outputs the action. So I'm determining it by this inductive procedure. Are you asking for some sort of more slick way to describe this, how you get this function out of the barcode?
Yes, maybe there is a. So first of all, A, B separately, are there symplectic invariants kind of? So I thought that A plus B is invariant quantity.
Right. So yes. So the A plus B is basically the Conley-Sanger index.
Yes.
So yeah, we know these values for fixed A plus B, and that's a symplectic invariant by the work of Seeley-Black for
So the set of all actions with given index, right?
Yeah.
And so now, so what is the logic? So you say that if this sets coincides for two domains, so domains, I mean, kind of coincide, right, up to reflection. So that's your statement, or that's what you want to prove.
Well, so what I'm proving is that the barcode determines the function. So if I have two symplectomorphic domains, then the barcodes are the same.
Yes, that's I understand. Yeah.
And then out of the barcode, but now I'm saying, right, well, let's just look at one of the domains. Out of the barcode, I can recover the function. So this sort of is an inductive procedure for recovering the function from the barcode, and it's going to give me the same answer on the other domain because it has the same barcode. So that's why the functions are the same.
I see. So so somehow this means that you have some inductive procedure which from barcodes reconstructs a function, right?
That's right.
So can you define this is some kind of function, or does it admit a simple definition? It's after all barcode, kind of. Or it's something very fancy. Does it? The question is whether this existent theory of persistence models, so you invented something new, or this is true only for very specific barcodes which you get here. So,
well, that's a great question. I don't know. So, but I was doing something with a very specific kind of barcode. So I don't know if you can say something nice for more general barcode.
I see. Mm-hmm. So if I will give you a barcode, can you tell me that this barcode belongs to a toric domain? Is a barcode a toric domain?
Well, I'm not sure I can tell you for sure that it does, but I can give you various conditions it must satisfy if it comes from a toric domain. So first of all, every action value has to appear, well, except for like the 0 ones, every action value has to appear twice as the top of one bar and the bottom of another bar. And you have to be able to arrange the bars like this in some order so that this action function is convex. So might be a little hard to prove that you can't, but maybe if you maybe you could, if you have an adversary, they could make some collection of bars, which you can't make a convex function like this.
I see, thank you, interesting.
Michael, I have a archaic remark. So the Benchy-Sakharov theorem is a kind of a precursor, right? When you take out the axis, the two disks over the axis, then you would immediately know without genericity and in all dimensions, right? So of course now one would like to try to put back the two disks, which may not work, but to put them, do you see?
Did they prove that for open domains?
Well, the statement is just that you have Tn cross a simply connected domain and another one. If then the two domains are symplectomorphic, then the two simply connected n-dimensional ones must be G, L, N, Z related. It's totally rigid. So here it would be, of course, just a flip. But of course, I'm kicking you at the axis.
In that case, you have the homology classes of the Ray orbits, which helps a lot.
Yes,
the boundaries of 3 torus.
Exactly.
Okay.
But then when I put back the cross of the disks back in normal form, which may not be easy or impossible, then I could immediately conclude from there, right? But maybe it's not possible because the map can be crazy near the boundary.
Right. Yeah. So if you can do what you said, then sure. Yeah, but these maps, these symplectic morphisms of open toric domains, so just take any Hamiltonian vector field and just stir it up as complicated a way as you want. Who knows what's going to happen?
Yeah, sure. The disk could be lousy. On the other hand, properly embedded two-dimensional disks are very flexible, right? You can move them back by a Hamiltonian vector field into a normal position probably by H principle. And then I could compose my map. Let's take one disk. I could compose my map with one that puts the disk back into normal position, then restrict the map, apply Benchy-Sakharov and glue back. At least in dimension 4. In high dimensions could be worse. I don't say it works. It's just kind of historical precursor.
Okay. All right. Thank you for telling me about that.
And it doesn't need genericity.
So Felix, you mean shape, right? Kind of.
Yeah, it is the good formulation is shape, but
yeah. And so in principle, shape can be defined even here, right? You still have kind of Liouville class, but right. So, but this should be done accurately, kind of. You need like some classification of Lagrangian tori, right? So up to Hamiltonian isotopy to be sure what Liouville class is, right? So what do we know in R4 about tori?
You mean the tori over the boundary?
Yeah. So no, just consider all Lagrangian tori inside the domain and bookkeep Liouville classes.
Yes.
Probably need some mark. So disk you are talking about, right? So we'll give you marking on homology, but maybe you can just consider marked torus.
Oh, and you don't want to, I see, you don't want to Benchy-Sakharov, but directly shapes.
Yes, just
okay.
Shapes as it is, yeah. It's nice idea.
So about the genericity, you strongly suspect it's not necessary, yeah, right? You did not try, Michael, to construct a counterexample.
No, yeah, I don't think it's necessary.
Hugo writes us that there was a work by Hind and Zhang about shape in this context. So Hugo, can you spell out what they did? You work in speak, okay. Nice.
Yeah, that's a sad
I would-
story.
Yeah, I would love to be also in cafe. I have another kind of philosophical remark that about possible generalizations, kind of, yeah. So there was an activity by Fomenko about various classifications of integrable systems. So I don't know if he did actually. Fomenko is in his school at Bolsonaro, for instance, right? And in principle, the method which you described would work with some more complicated integrable systems, so not just Toric domains. Okay, and it could be kind of so first thing which comes to mind is like surface of revolution or will surface and on two-dimensional torus, right? So I mean there are integrable systems, and by the way, big open problem which still exists that there are no that this is all. So if you consider like Riemannian metrics on the Tori, even two-dimensional torus classification is open for I mean since my students' years, yeah. So it's at least. And what you are saying could be I mean this tool could work for to push a little somewhere this classification. I don't know. I mean some imagination is needed.
Okay, cool.
Okay, so thank you, Michael, again. I'm getting up started.